Hello, this is Chip Westerby, Sales Manager for Benchmark Measurement Solutions, formerly known as Turner Design Hydrocarbon Instruments. Today's going to be a little bit of a different presentation than our normal micro application discussions. What we're going to talk about today is a presentation from a roundtable at the February Produced Water Society conference. Most industrial and produced water processes require oil measurement of water discharge. But the oil can be in different formats. It can be dissolved within the water. It can be a free oil droplet. It can be emulsified. There's different ways to describe how the oil and water mix together. And today we're going to talk about what those differences are, how to measure them, because defining what needs to be measured in the water is important to figure out the best method to do the measurement. There are many different ways in which people use to describe how oil and water are mixed, or the nature of the oil within the water. In many ways, the oil can be described as a dissolved oil or dissolved organic, an emulsion, a rag layer, oil droplet, free oil, dispersed oil. And all these things have what seems like very unique definition, but they're actually quite blurry. Because if you think of something that's actually dissolved in water, think of something like sugar or salt. You add it to water, it dissolves, it becomes completely chemically mixed within the water phase. However, oil really doesn't behave that way. In many cases, very, very small droplets of oil will be freely suspended in the water phase, but they're not actually dissolved. A lot of people refer to those as emulsion. Other people define oil by the size of the droplet, by the micron size. Is it a 0.1 micron, 1, 5, 10, 15, 20 microns? You can figure out how large the oil droplet is. But in reality, the process, the tank, the type of device that's used to remove the oil from water, or what the regulatory analytical measurements are, those actually define what the oil is or what format the oil is within the water phase. And that's going to be a big chunk of our discussion today. So the first thing we're going to look at is three different types of water treatment systems. One is basically what I call just a simple gravity separator. This could be some type of storage tank or a tank that has a little bit of technology inside of it, like a gun barrel tank, or it could be a coalescing filter or coalescing pack of material. All these things are designed to force oil droplets to attach to each other or come together so they can be separated a little bit faster and a little bit easier. There's other technology that I call enhanced gravity separators or enhanced gravity systems, and these are devices that effectively spin the oil in the water at high rate so that the gravity is increased. It might be a 5 or 10 gravity or 10G centrifuge, and then all that does is make those oil and water droplets, the oil droplets, come together a little bit better so they can be separated. And lastly are filters or membranes. These are physical devices that have the ability to remove very small oil droplets by physically removing them from the water so that they can be passed down the process into a waste. And each of these filters or membranes will have some type of size, some type of pore within them that will allow things smaller than that to pass through the filter or the membrane, larger particles, larger oil droplets not to be separated. So one thing to kind of conceptually think of here is how do these systems really work and how are they different? Previous boss of mine, Gary Franson, when I was at Agar Corporation, what he used to tell people is if the oil will float, he can guarantee it won't come out the bottom of the tank with the sensor technology that they had. What does that mean? Well, if you think of a simple storage tank, maybe something as simple just as a bucket. You take oil and water, mix them together, pour it into a bucket or a tank, and it'll sit there. Oil and water will separate quite quickly. The longer it stays in that bucket or in that tank, the more separation will occur. But you have to imagine that if you had a gasoline tank that you're using for your yard lawnmower, and there's a little bit of water in that gasoline tank. Pour all the gasoline out, there's a little bit of water left in there. That water is going to be pretty gross. There's going to be gasoline in it. It's going to smell like gasoline. It's going to might be a little bit of brown um, color to it. And people understand this. While gasoline and water do separate easily, readily, they separate almost as fast as you can mix them together. The water that's left over after you remove any of the gasoline, you don't want to drink that. That's not pure water. Well, the time taken to separate has already occurred. The gasoline has floated. Anything that's left in that water that makes that water a little bit of brown, it's not floating. It will stay in the water phase. It will go at the bottom of the tank as water. Things that can affect this are the amount of solids. If there's a little bit of sand, a little bit of rust that oil will adhere to, that could make the oil sink or be neutrally buoyant. Temperature has a big effect of this, the chemicals used, and then any structures within that vessel can affect this separation. The image that we have here is from an offshore oil platform, and I really like this type of image because every time that you see a presentation or a discussion about oil water measurement, oil water separation, everybody's going to have a picture of a bunch of different bottles, and the one on the right will be dirty black, and the one on the far left will be nice and clear. So look how my water treatment system is working. And so it's just a common image that we always see. In this particular image here, the image on the right is what came out of a hydrocyclone on an offshore oil platform. So you took oily water, ran it into a device that enhances the gravity, spins the oil water very quickly. Most of the water is separated, goes out the bottom, and the oil goes out the top. That water is not clear. There is still residual oil left in that. So even though we have enhanced the gravity of this sink, we've made a pretty high and efficient separation. That's not pure water, but it's also stable. There is no clear interface. There's no layer of oil at the top. This is a stable emulsion. That's oily water that will not be separated. The left-hand picture, that is after a gas flotation system. So gas bubbles are induced into the water phase. Those gas bubbles will force oil to the top, and then the oil can be skimmed off. So it's cleaner, more oil has been removed, and now we have a relatively low oil content water. But you can still see that's not pure clear water. There's still something left in there. This is also very stable. There's no interface, there's no sheen, there's no oil surface at the top. So in both these cases, anything left in that water is going to be an emulsion, but they're different. They're different because of different water treatment systems that is removing the oil. So what the definition of the emulsion is different from this hydrocyclone to this gas flotation cell. And that's the crux of what we're talking about today. So we're going to talk a little bit about why and when these differences is important and what we can do about it. So one of the times that this is really important is if that water, after the oil has been removed from it, is injected into a disposal well or injected into a enhanced oil recovery well or somehow recycled through a formation. In this case, the water will be pumped down into a well, and at the bottom of the well there's going to be a formation, a rock formation that the water will be pushed into by a high pressure pump. The size of the holes, the porosity of that rock formation is a big factor in the efficiency and how much water can be injected into that. So the oil droplet with solid particle sizes have to be smaller than the holes within the rock. If too much oil is pumped into the well, then the well has to be cleaned out. There has to be some type of work. This could require a complete shutdown of the well. Um, could be some chemicals or mechanical methods of cleaning this out. So if you have a injection well, knowing that the oil droplets and the solid particles going into that well are small enough to fit in is a very big factor in the efficiency and the function of that well. Another reason for knowing the nature or the size of the oil and solid particles in your water is to confirm that the water treatment system is working correctly. The previous example of the hydrocyclone and the gas flotation cell had different water qualities. And if a operator buys a hydrocyclone and says, we want you know, less than 10 parts per million of water in the discharge of this hydrocyclone. But the oil droplets feeding that hydrocyclone are so small, the hydrocyclone can't remove it. You're going to get something that's much, much higher in oil content than is capable. So often, a water treatment system will have a rated separation efficiency or rated removal down to some concentration, depending on the size and nature of the oil droplets. So it's not just an oil concentration limit, but it is also a nature of the oil droplet limit. So as an example, previously worked on a project where a storage tank that had some water at the bottom of it, the water was removed and the water tested for oil concentration. And in this particular case, the result came back at 30 parts per million, which meant that the customer expected this water treatment system to always be able to achieve 30 parts per million water quality by just having it sit there. But the temperature of that water, the solid content, the amount of time, all these things had huge impacts on the water quality, how much oil is present. And there's no way to guarantee 30 parts per million time and time again. In reality, between 30 and 500 parts per million is very likely in water quality out of a storage tank. It could be even higher than that, of course. There's a lot of different factors here. If you have a gas flotation cell, we talked about that just a little bit earlier here, they can be between 10 and 50 parts per million, again, depending on the nature of everything. And then when we get into membranes, places where there's absorption or physical removal of certain particles, those can be designed to have a oil content way less than 1 part per million, very small particle sizes. So there's a lot of different factors in how water treatment systems can be performed and tested for that. So to know how much oil or what type of oil or the nature of the oil that's in one of these water samples, there's some type of oily water analysis that's needed. The method that is used to analyze that can be manipulated to tell you a little bit of what the nature of the oil is. So if we look at the picture that we've got here, sample analysis is very, very common. There's a lot of different technologies. There's different ways of handling it. If we look at the picture on, or the bottle on the left, we have a oily water sample. There's a fine layer of oil that's floated to the top of the water, and then there's oil that's coated to the walls of the jar. The water itself is still quite cloudy. It's got a lot of turbidity to it. This is oily coated solids that are neutrally buoyant, and they stay in the water phase. Picture on the right has been treated with hexane. So a known ratio of water to hexane is added to this bottle. The bottle is shaken for about 2 minutes or so. Once it's set down, all the hexane's floated to the top, and we have an oil-rich water sample that has virtually all the oil present in that original water phase. However, the nature of the oil that's in that water can be one that doesn't allow hexane to extract it. There can be water soluble organics. There can be different things in that water phase that are or are not soluble within hexane. So we want to have a really easy way to prepare these things. We want to have a way that meets the treatment technology capability as well as the process capabilities. So we're going to talk about ways of manipulating the samples here. So one of the important factors in how to make this measurement is in defining the type of particles or knowing what the type of particles that you want measured are. There are many different ways to manipulate a water sample to produce data that is helpful for operators or engineers or commissioning water treatment systems. Most of the time, an operator will develop a method that works best for their process and their purposes and standardize on it. But in some cases, to glean just a little bit more information about what's happening in the process, the sample preparation procedure can be changed. Adding of acids, using a polar absorbent, using a different solvent, or using a certain filtration will affect what the analysis is. So most government regulatory laboratory methods use an acid in the water to allow the hexane to extract any of the organic acids that are present in that water. Um, it doesn't have to be any specific type of acid, but getting the water to a very low pH makes the solvent much more efficient at removing organic acids. So if you want to know how much organic acids are in your water sample, making a measurement with and a measurement without the acidification process will tell you organic acid presence. A lot of these regulatory methods will require a low pH of the water, but then they will um, have the solvent pass through a polar absorbent material that removes the organic acids. So similarly, you can make a analysis of a solvent that has or has not been treated by a polar absorbent material. Other customers, other operators, or other water processes will have the oil with different affinities for different solvents. So hexane is very commonly used. It's a very good solvent, but it does not extract all oil in all cases. Toluene is often much more efficient at removing oils, especially very heavy oils with a lot of asphaltenes or waxes or things like that. So an operator could choose one solvent versus another or change solvents and see what happens different to the process to tell them a little bit about what's happening there. Lastly, and what's a little bit more sophisticated, is that there are very small filters. Think of a filter that sticks on the end of a little manual syringe, and it may have a pore size that is like half a micron, 1 micron, 5 microns, 10 microns. If you want to know if the water process has a certain amount of oil content below 10 microns, you would use a 10 micron filter, pass all the water through there, make a measurement of the result, and it'll tell you how much of the process is below 10 microns. This is very helpful if you have a water treatment system that removes everything larger than 10 microns. You can't expect that water treatment system to remove small particles. It's not designed for that. So analyzing the sample to know what is or isn't in there by particle size tells you if that water treatment system is meeting your expectations or not. A more sophisticated and much more detailed way to measure oil and solid particle size is through an online particle imaging analyzer. These are, in one case, very simple, but also very sophisticated analyzers with a onboard high-speed, high-resolution camera and software. Multiple images of a water sample can be taken. The water can be passing through that rapidly, and every particle in each image will be sized and typed. So these devices will be able to look at a water sample and say the oil concentration is 10 parts per million. 30% of all the oil droplets are below 5 microns, 50% of all the oil droplets are below 10 microns, and 75% are below 30 microns. Same thing with the solids. They can tell the concentration and the distribution of those solids. If there's two different types of solids, they can also tell the difference in two different types of solids in many cases. So these are able to produce all the data that an operator might need without the operator having to do any sample manipulation or have any sophisticated chemistry available. Water passes through it, the data is generated, water goes into discharge. So regardless of what the operator needs or what the process needs, there's about 4 or 5 different ways of preparing samples and looking at water samples to know what's in there. So I hope that you learned a little bit more today about how to determine if you've got emulsions or soluble oils or free oil or other things in your water. If you need some help, please let us know. We look forward to talking to you.